So honestly, I'm just recording to document like my curiosity, I guess, or I don't know. You know what? I'll figure out later. I'm doing a deep dive on everything and nothing at the same time, and I was looking at a video which I was supposed to do, like brush my teeth and watch, but actually I didn't finish it, and it wasn't this one. This
It
one.
is now
Oh,
my
this.
pleasure and
Oh,
great honor to
what?
introduce our second.
Thank you. It was. Oh my God, where did it go? Where did it go? Oh, it was this one. I started from this, and then it kind of branched off, as you can see, from the many tabs. And yeah, so if you wanna watch, watch. If not, no. It's more of a documentation to see. I don't even know what. I just wanted to record, to be honest. I don't really have. But yeah, so currently I'm trying to understand uh, like the whole thing that I was looking into was LLMs and artificial intelligence, which is super interesting. But I want to see because I've had a feeling that what they were trying to do is what most of the time is to mimic the human brain, but there is a critical thing with the human brain which we are not using in our current models, as we are using the this von Neumann architecture in all the computers with control units. So this is our central CPU, and this is our memory unit, our hard drive, and this is highly inefficient compared to how our brain computes. Obviously, uh, people say, I guess we don't have a hard drive, but we do have areas of our brain which do impact our brain. But also a critical thing is with neuron and synapses, which I don't have here, which sorry, I'm spoiling everything that I've been like the synapses which store the memory within the neuron or something. But I'm really not a neurosurgeon, but I find it fascinating. I try to understand. And then I realized I actually have holes in my knowledge because once they were trying to explain how neuromorphic computing at scale works, I was lost because there is something called in one video. Actually, it was kind of poor. It was on computer file. I don't have it here anymore. It was somewhere before this. It was um, they said there's a new thing which they found in like 2008, which is a memristor, not a resistor, but it's a memristor, which somehow stores memories. So there's like a spike of current and voltage, but somehow it takes a snap, and due to that it creates a memory. God knows how it does it. I just realized that I didn't even know what voltage was, so I was looking at that, and then I realized it's what's the push within this current, and it's the difference between the electrons between the cathode and anode, and the bigger the difference, the bigger the voltage. There's still gaps here, but we're making do. And then I realized it says that all this, it says that, for example, um, some particles are positively charged, negatively charged. And my question was, what does positive and negative charge even mean? And I think these holes are made for school, or I forgot where from. But then it comes to the question, what is charge? And the explanations that I got is that it's um, this was another question, but the explanation I got for that was that it was I felt to me like a cop out, even though it shouldn't. It was I wish there was like a way to uh, find the original stuff, but it was a kind of a cop out. Oh, here. So look, this is the video I was watching, but it was video because I can. It says positively charged particles have a deficiency in electrons, while negatively charged objects have an excess in electrons. But it's escaping the term of what does charge even mean here. So the closest thing here was sign convention, and it says positive and negative are just labels assigned by scientists. These labels are consistent, meaning that objects with the same sign repel each other, while objects, okay, great, but this isn't magnetic charge. I think so, and this is also, I think, where I get the whole, which this kind of looks like magnetic actually once I say it. I guess electric charge. Um, which is actually mean. But what does it mean for something to be positively charged? Obviously, they attract or repel each other, and this really looks like a magnetic field with the same things. But what does it mean? Like, what's causing this behavior? And that's the question I'm currently looking into. Will define the defining charge, not the what how it behaves, but the actual essence of it. Um, so if we look here, isolate system, the amount of positive charge. Electric charge is carried by subatomic. Okay, and these would be. Um, like, what I realized that through all this research, I know nothing. I know nothing. Like, and then there's the question of up quarks, down quarks. Like, what, like, what's this? And then this go. I guess this goes to, like, they have charge here. They have color charge. Like, what is color charge? There's a color to a charge. What, like, what is a color charge? So there's positive and negative, and then there's colors of quarks and gluons. I don't know what a gluon is. Massless elementary particle. What do you What do you mean it's massless? I thought I thought that we have no yeah so sorry sideline. I was looking into the very simple equation of V equals IR here, and I was wondering if we can have a graph that has here VI, because in like one of the videos the guy did IV. I don't remember what it was, but it was like this. But yeah. Anyway, so I was looking here at the if, and it's possible, but obviously I didn't think. I tried to do it like mathematically, and then got that obviously resistance has to be infinitesimally like low because of this here, where you do I equals V over R, but then you can change it to V over 1 times by 1 over R. So obviously you can see that um, for current to be infinitesimally high, this has to be infinitesimally low, or else this number will be small here, which will make this smaller. So anyway, I'm very bad at explaining, but that's also something that I'm trying to improve on is explanations, or just expressing myself. But I thought, okay, I understand that there's a um, like a contradiction in quantum physics and classical Newtonian physics, but massless particle. I mean, we have F equals ma. This is the mass, and if this is 0, then the F should be 0, correct? Masses. This mediates the strong interaction between quarks acting as the exchange particle. What? Ah, but so stupid. What is vector boson? I don't know this stuff. What is this? It's spin. So you're telling me it's spinning like around? But yeah, so this is what I mean. I go from one thing, right, and I'm just going from charge, and I end up at vector boson. Neither do I know what gluon is. It's somehow a type of massless elementary particle. This sounds like absolute nonsense to me. As a, how can something exist without a mass while also being a particle? Let's see what Copilot has. I'll ignore this question for now and create a new chat. How is this possible? A type of massless elementary particle. How is a particle able to be massless? I know there's like the thing with like photons behaving as particles and waves, but then the question is, okay, that I don't even know that. Okay, so I can't answer that either. A massless particle is one that has zero rest mass. Rest mass. See, look, and then what does what is oh, what is rest mass? Rest mass, also known as invariant mass, is the intrinsic mass of an object or particle when it's rest observer. Its minimum mass. So I guess for a point particle we can define rest frame of the particle. Yes, that's fine, and I guess I'm assuming that due to this existing definition, mass changes as the particle moves. Secondly, the equation is incomplete. E squared equals m squared, c plus p. What's p? Here is m is the rest mass of the particle. P is its momentum. So thus the energy of a particle had two factors: a rest mass factor here. Okay. So in this case we could put 0 here, which in turn this would turn into 0, and then momentum. Kinetic factor. Okay, so this is while it's moving. And I guess you add obviously the base to the movement, which makes sense. I'm not gonna ask why this is squared, that might take me on another tangent. But that is also a, but then it will come to the whole explanation of note that when the particle is not moving, that is p equals 0, that equals reduces, yeah, okay, that's it. The rest mass of the clock cannot change due to linear motion. But since the clock is moving, it has more kinetic energy than the clock which is not moving. Thus it has more energy and not more mass. But then why do people say that moving clock has more mass? This is a result of some confusing terminology. We define the relativistic mass of a particle So that E equals m relative c squared. That means that if the energy changes, then the relativistic mass also changes. Thus, when people say that the mass of a rotating clock has increased, they actually mean that the relativistic mass has increased. Note that physicists don't use the term relativistic mass. No way, bro. Realize that the rest mass of rotating does change. What do you mean it does change? If it Yeah, exactly. That does not help with the question I have is so does photons have zero rest mass, right? Yes. Yes, this is a good question. What? Okay, this is even crazier. A photon inside the medium isn't a photon anymore. I'm gonna put that in this. I have like interesting findings, and this is something. What? But light. Okay, if we say let's see what's this here. Isn't this an assumption? Hold on. Let's see what they say here. Massless famous equation. Yeah. Okay. And this is back to the same thing we had before. Uh, for massless particles, and this means that the energy comes from their momentum. They never stop. Massless particles like photons and gluons always move at the speed of light. Since they can't be at rest, the constant rest mass does not apply in the usual way. So because it can't, and then in brackets, in theory, what the carries a strong nuclear force. Whoa, what? Nuclear? What does nuclear force mean? I don't know anything. Gluons are massless in the standard model, but because of the strong force's complexity, like confinement, they never exist freely like photons do. Strong forces complexity like confinement. What? Okay, so this binds. chromodynamics. What is quantum chromodynamics? Why does this look like toys? What is going on here? This stuff is way too complicated for me right now. Study. Oh, cause this is back to the color. Yeah. I got. Whoa. This is back to the color charge. No. Quantum. I got it. It's clicking. But it determines how quarks and gluons interact with strong force. However, rather than there being only positive and negative charge, there are three charges, commonly called red, green, blue. The three, what's it called? Independent. I forgot the color thing now. Listen, there are also three anti-colors called anti-red, anti-green, anti-blue. Unlike electric charge, color charge is never observed in nature. In no case, red, green, blue also combined is a form of a color-neutral system. For example, three quarks making up any, I don't know what that is, university have three different color charges. So they all have blue, green, red, but is it actually blue, green, red, or are they using it as description like positive and negative? The two quarks making up any meson university have opposite color charge. Okay, the color charge of quarks and gluons is completely unrelated to the everyday meaning of color. Thank you. Which refers to the frequency of photons, the particles that mediate a different fundamental force. Like the term color and the labels green became popular simply because of the loose but convenient analogy, the primary colors. There we go. That's what I was looking for. Primary. History. Yeah. It's vague. Someone later. Internal degree of freedom of the triplet model and advocate a new field theory designed as quantum chromodynamics. This is the thing that we're talking about. And the interaction of quarks and gluons within hadrons. In German schematics, each quark and gluon has fractional electric fractional and carries what came to be called color charge in the space of color degree of freedom. A quark color can take one of three values: red, green, and blue. 2 seconds, I'm just gonna get Sprite. It's kind of hot here. Bear with me a moment. Okay, I got a little snack and anti-quark, one of two anti-colors. That doesn't look like a color to me. Net angular momentum, so zero spin, right? Yeah. There's only one spectral line of a single step. Okay. Splitting of spectral lines to double that. Okay. This looks. Oh. Okay. Okay. Got you. Got you. Sorry. Sorry. What wonders me is how do they figure this out? How does one? This entanglement thing is crazy. Particles in single states do not need to be locally bound to each other. Thank you. Just checking. For example, when the spin states of two electrons are correlated by the emission from a single quantum event that conserves angular momentum, will the electron remain shared single state even as the separation space increases heavily over time? Even philosophical. Seeing such states contribute importantly to the theoretical experiment exploration and verification of Nowell's quantum entanglement. And this is what um, I was looking at before. Oh come on. There's quantum. This is this is crazy that this actually exists. Look at this. Measuring the state of one entanglement qubit instantaneously influences the state of the other, even if they are light years apart. How is this possible? What the like? Hmm. Single source. Hold on. We are connecting the dots slowly. Oh no, it's singlets. Sorry. We are indeed not connected. Not all particles are entangled. That's true that a particular typical particle is entangled with many others. Many. Too bad me select bar. I'm not likely to. Oh wow, really? I wouldn't think so. Right? You have so many. I don't. I mean, this is kind of self-intuitive, but this in the first place to exist. What does what like where are you? Because even in the theory of this also is that light goes this way, right, and the photon, but once it passes through a medium, it's not a photon anymore. A photon. How? So I have questions on. I haven't even gone to what is charge. I haven't gone to the nuclear charge. I don't know what that is. Color charge. I know that's just a phrasing for it, but what does it even? I guess we were on it. I guess this where color charge. And also, how do free particles exist in the first place? Do and you know what's fascinating that I found was that we can't. There's a couple things which I have here, shall I say. So Turing proved, actually, like in 1936, that not all mathematical problems are solvable by algorithms, which was really interesting. And then, obviously, I went to numerical computers. That's about it. But this part of um, I mean, entanglement. I don't know how this is even possible or it being figured out. Oh my god, like this symbol scares me. What is that? Like, what is going on here? A coupling constant and a charge are different but related notions. The coupling constant sets magnitude. Quantum electrodynamics. Oh. Light and matter, light and matter. Were we on it? No, we were on something else. This constant. But well, what is the Feynman diagram? Notation, mathematical expression of the subatomic particle. The scheme is named by American Richard Feynman. I've heard of this guy before. Calculation probability amplitude. Theoretical particle physics requires the use of large complicated integrals over a large number of variables. Integrals graphically. Give a simple visualization of what would otherwise be an arcane abstract formula. So you have an electron hits on the positron. What? Anti-electron. There is an anti-electron. What? Like, what? This blows my mind. Like, we have so much. How? But in theory, right, if we have anti-electrons, anti-protons, and anti-blah, blah, blah, and we were in a place which has infinitesimal space, right, and like time, wouldn't there be a point where me, the Jacob here, would be an anti-Jacob? Or this is completely two different things? So we have electric charge here. This may be a clue of what charge is. I'll keep it separate because actually I think charge. I think we might find it without even searching on LLM. Spin of a charged particle. The G factor, gravity. The magnetic moment. Magnetic a moment? The gyromagnetic ratio. Okay. That's what we're talking about. Where mean is the magnetic moment resulting from the spin of an electron. S is its spin angular momentum, while is the Bohr magneton. In atomic physics, the electron spin g is often defined as the absolute value GE. What? And if supersymmetry is realized in nature. Oh my god. Well, what is supersymmetry? It's a theoretical framework that the existence of symmetry between particles with integer spin bosons, in particular with a half-integer spin fermions, proposes that every no particle there exists a partner particle with different spin properties. This is exactly what I was talking about. The anti-me. There have been multiple experiments that failed to provide evidence that exist in nature. The hierarchy problem. There's a hierarchy problem. I'm saying the large discrepancy between aspects of the weak force in gravity. There is no scientific consensus on why, for example, the weak force is what is weak force. Weak interaction weak force or nuclear is one of the four fundamental interactions with the other being of electromagnetism. The strong interaction, it is the mechanism of interaction between subatomic particles that is responsible for the radioactive decay of atoms. Oh yeah, this is also a question, right, that pops up. I think I'm gonna just write notes because uh, questions. Why and how do particles decay radioactively? That's one. Two. Oh, I guess I have to press space on this one. Two. What is color charge? I mean, is it do with spin? What is charge? What is nuclear charge? What is charge in general? This question I haven't got an answer. Why do free particles exist? This might not even have an answer. Um, can a anti-Jacob exist? And if so, how would he look if supersymmetry is proven to exist? In theory, with infinite amount, couldn't the symmetry exist? No? Intuitively thinking, I'm saying yes to that answer. Because if you have like a infinitesimal space, I think that could be possible. Why is spin so important in quantum mechanics? In 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 yeah, quantum. I'll just write quantum. Then there's what happens to a photon when it passes through a medium. I think we should tackle while doing this. You can see that I'm jumping very quickly from one thing to another, which is good in my opinion. But we don't get anywhere, so we get everything but nothing at the same time. So I think the best would be structuring and going one by one. And then if I have any other questions that trigger me to, like, right click on it and ask what is it, keep it on the list to check out later, but not necessarily now. So did I have any? Oh yeah, and then mem resistors. How do they work, and are they even useful? Okay, I guess we'll start with the first question of of why and how do particles decay? I was not. Yeah. See, and my brain already shoots. Before I even started reading, I already have a sub question. Then I had the question: if decay, if I think they call radioactive decay, didn't exist, could never die? Then second, I had if supersymmetry exists, couldn't we reverse radioactive decay, or is it a one-way street? Okay, I'm gonna cheat this and go on the confinement, like what is a strong force which is what is a weak force, like 110 to the power of 24. Okay, so let's see what the AI has to say about this one. Hey, what? Come on. Let's do a new one. And let's do this one. Why do particles is this true? Is this called radio? Unstable. Hmm. Strong nuclear force. When repulsive electromagnetic force overpowers the strong nuclear force, especially in the large neutron-heavy nuclei. How does this happen? How does this...
Hello and welcome to the video on radioactivity. In this video, we will cover natural radioactivity is a phenomenon that occurs in certain elements such as uranium, thorium, and radium. These elements have unstable atomic nuclei that spontaneously decay, emitting alpha, beta, and gamma radiation. Alpha particles are
Oh, I'm completely on the wrong subject. I thought we were talking about... What's it called? What is the decay... The... So this is two different ones. Two separate terms. Yeah. Okay, I got you. Okay, that's fine. I was rather... The question that I was rather asking is more... That... Actually, the question was on... I misinterpreted what I read. It was if... Particle. Why? Whoa. So everything has life and death. There's nothing that doesn't. Yeah, I know. Yeah, this is interesting digital. What? So it does say particle that... Oh, that's true. Systems naturally move toward disorder. That's very interesting. I guess actually putting a structure to it makes it like, I don't know. It doesn't suit me. I prefer the chaotic. Sisters, I'm going to Divergent, and you know what? Let me just go on this ride. What's the point? Um, is this fundamentally true for all of life? Second law of thermodynamics says this. That is crazy. That's what? But how was that proven? Like, it does make intuitive sense for things to become chaotic. I wonder how the world would look like if the second law of thermodynamics was opposite. Yeah. Okay, so it's a balance we're giving it. Oh my god. That's really cool. I didn't know this. This is a highlight. Like, just say entropy is like, oh, okay, but I'll put that in. That's pretty interesting, I'm not gonna lie. That's interesting. Okay, well, maybe I didn't answer the question, but maybe the question never did answer them. Oh, thank you. Selectron. I thought it's a positron. Selectron. May refer. Slepton. I'm a Slepton. Super partners. Super partner. What, they're married? What's going on here? Oh, it's like, yo, you know what? I'm not doing strong interactions. Okay. Smooth. Stop. What's going on here? How? Is like the way? I'm gonna ask. Is this conversation jumping? I'm gonna put it here. Quantum physics. Did this name come tower ism or not? Probably not, but it'd be pretty cool. Great question. No. No. Oh, proper time and return. What? There is the Tower of Physics? Okay. What? That is insanely interesting. Philosophy of science. But quantum mechanics, you could, dude. This is so interesting. I don't know. New age. Yeah. Okay. But that is super interesting. Maybe you can. I think the quantum physics has, as far as we can go, the answers to everything. I mean, I don't know how close we can get, but it's as far as I think we can right now. I mean, I'm pretty young and ignorant, so probably I'm not fully correct, but definitely not correct. Probably completely wrong, but yeah. Like the second of uh, thermodynamics. At least we try. Consciousness causes collapse. What is going on here? This is what I mean. It's discarded here, but I mean, I don't know anything. Go ahead. John von Neumann again. And then they're back to singing. Okay, that's interesting. Mm, that's very interesting. It has been argued that the results of delayed choice quantum what? Permanent because of an entrance pattern would only be visible. Whoa. The formalism. What is formalism? Oh. Okay, I think we're gonna take a break here and come back. This is a little bit overwhelming now. So see you guys after.